Okay, let me get started. I'm going to announce first, I broke my eyeglasses. I was taking off a mask and I jostled them and they fell to the floor and they broke. So I took them to the store. They said they would, they offered to fix them, but it turned out that all they could do was send them to Denmark to be fixed in Denmark. And so until then, until they, actually I've ordered a backup pair, but until then I have these glasses which do not work very well. And so I may periodically sort of take off my glasses and peer at the screen to see what I'm doing. And so sorry about that. Anyway, so I want to finish this discussion we've been going through for the last couple of weeks on, so this shows that if we solve the axisymmetric order equations with initial data for which the vorticity is concentrated around a ring, then we've already seen that at all subsequent times it continues to be concentrated around a ring of roughly the same radius. And we want to see that, we want to characterize the velocity of this thing. And so the velocity is, if the ring has 4 pi and has circulation, if the ring has radius 1, sorry, and has circulation 1, then the velocity will be of order 1/4 pi, I believe. And so this is this background. We considered the general, the axisymmetric order equations of those will have this form. We considered, we wrote the Biot-Savart law in this framework. We expressed the energy in this framework. So let's, right, and so there we had this stability or this vorticity concentration estimate. And so these things up here will be the assumptions we make on the initial data when we solve the equations. And remember, these are preserved by the flow. And under these conditions, our conclusion was that the vorticity has got to be concentrated, and it's got to be concentrated basically at the distance 1 from the origin, up to small errors. Okay, so now we consider the axisymmetric equations of that swirl with initial data as described above. And the point is that all of these hypotheses are preserved by the flow. And so if this is true at time 0, it's true at later times, and the conclusions then hold for every time. That's the first part here. These conclusions hold for every time, and then we have this approximate center of vorticity, and I can't see this approximate center of vorticity called, there it is, x epsilon star, and this tells us we know that the r component is basically constant, it's basically 1, and the z component behaves like this. It moves with velocity 1/4 pi. And so we started proving this. We proved, well, yeah, so this is the basic identity here. And this just comes from the equation by rather straightforward computations. And so the idea was to use this to see how the vorticity is evolving. And so so first we using this, we proved that this approximate center of vorticity stays within, it stays, so we know that the r component stays close to 1, and we showed that the z component stays close to where it started, say a distance less than 1 from where it started for times of order. We have a uniform time. There's some time capital T such that within, if this tau variable is less than capital T, then the vertical distance we've moved is less than 1. Remember, we had to rescale time by some logarithmic factor, and so the tau variable is this rescaled time factor. Okay, and so right, so we showed that for times of order 1, say, the approximate center of vorticity would stay within this region A. In fact, it would stay bounded away from the some positive distance away from the region B. Okay, and then the so then the program was to use this identity, which appears again and again, to control the motion of the center of vorticity. And okay, here's the identity. So we have, actually, let me write it like, well, so our plan is, we have this identity d tau of the integral of phi. So here omega epsilon is the vorticity coming from a solution as described above. Dx is dr dz, we're going over the half plane. And this is equal to, let me write it like this first. Okay, and so both this and this are 2x2 matrices. The first one has these derivatives arranged in a certain way. So we take the gradient, we rotate by 90 degrees, and then you take the gradient of that thing. And then the second one, the entries just ui, uj, the coordinate velocity, the quadratic terms in those. We have this, and we know that, and we considered a very specific test function phi, who, where was phi defined? It was defined up here. And so we know that in this region, right, in the region A, phi is just linear. It's just actually this phi is just a linear function of the z variable. It's z minus z naught, where z naught is the center line here. And z naught is the initial z component of the vortex ring. Okay, and so so in this region, in this green region, the test function is just a very nice linear function. It's supported in the bigger region, and so its second derivatives live in the region B. And okay, and so our goal is to then look at the right-hand side of this identity for phi as just described, and knowing what we know about omega and about u. And so we know about omega is these vorticity concentration results, and we know that the center of concentration is in this region, and this is bounded away from B. Okay, and so our goal then is to understand what number we get here on the right-hand side for omega and thus u and phi as described above. Okay, and I gave a very hand-wavy argument last time, showing how this should go. And but the point is that we well, so what I'm going to do is I've almost finished typing all the details of this. They're a little bit nasty, and so I want to just talk through the proof, and then I'll leave the details. I'll post them online within a few hours, I hope, on my webpage. And okay, so we must understand. Take this off. This integral of dx in the half plane. So phi described above. And here u epsilon is the Biot-Savart kernel, say the axisymmetric Biot-Savart kernel applied to this omega epsilon. And omega epsilon is well, we'll recall what it is. Okay, omega epsilon as described above. Okay, and so what I'm going to do is I'm just going to start sort of slicing off pieces of u until I get the essential piece, which will contain what I want. And so first, let's define. I want to divide the vorticity into two pieces. And so what we have with this, what we know about the vorticity is that there's the center vorticity x epsilon, or x epsilon, like we called it. And we know that if I look in the ball of radius r times epsilon, centered at x epsilon, that will contain all of the vorticity, which is integrates to 1 up to an error of order 1 constant over log r. And so let me let omega epsilon be omega epsilon I plus omega epsilon O. So I and O stand for, say, inner and outer, where omega epsilon I is the vorticity, the whole of vorticity times the characters function, the function which is 1 on this one set I'm about to describe, in the set of points x, such that x minus x epsilon, the center vorticity, is less than epsilon times log epsilon. Okay, and I should say, so in the theorem, the theorem, okay, describes a solution omega epsilon of x and tau, and u epsilon with x and tau. For all of these computations, the time variable tau is irrelevant, and so let me just imagine it's fixed, and I'll not exhibit tau anywhere. So all that we need are the properties I'm about to write down. So we've shown that and so then omega epsilon O, of course, is the difference between omega is omega is everything else. Omega. So we have shown that we know that, okay, by assumption the integral of omega is 1, and the integral of, and this was the concentration result, the integral of omega epsilon I is bigger than 1 minus a constant over log of r, which is log epsilon. Okay, so that's something that goes to 0 very, very slowly, but it goes to 0. And that's all I care about. And so the other part, omega epsilon O, is less than this. Okay, and so first, and so I look at the part, and so then we'll say, let's also let's make this smaller. If we can, hopefully your eyes are better than mine. Oops. Now we'll let U be U epsilon O plus U epsilon I, where you know, each one is the U epsilon I, for example, is the axisymmetric BSR kernel applied to omega epsilon I. Okay, what I want is I'm trying to compute this quantity on the right-hand side up here. And for this, I'd like to imagine that U is really just a, you know, a character function of a ball multiplied by a certain constant. I can't quite do that, but I'm saying, well, we can assume essentially the support in a small ball, and then the other stuff will give negligible errors. That's what I would like to show. So, okay, and so so once the vorticity lives in a small ball of radius epsilon log epsilon, then I can estimate pretty explicitly what the associated well, my goal is to estimate pretty explicitly what the associated velocity field looks like. Okay, and so my claim is that, and remember all of the, let's go back up here. Right, so whenever I compute these L2 norms of the velocity field U, I'm always dividing by log epsilon, because I know that the total energy is of order log epsilon. I divide by log epsilon, I get something of order 1. And so I'm going to slice off all these little pieces, and all the little pieces, well, they may grow, but all I need to show is they grow more slowly than log epsilon. Okay, and so my claim is that the integral of, so the L2 norm always has a factor of r in it, q epsilon O squared Okay, so how do we do this? Well, okay, let's note so note also from here, I can see that if I multiply by, so the things I know that for omega, I know this is true. And so I can see the same will be true for that when I look at the part from this vorticity concentration near the center of vorticity, because I know that R is close to 1 there. And so R is within like log epsilon to the -1/2 of 1. And so also I think this is again this, and there are other terms of order log epsilon to the -1/2, but those are smaller than the error terms I've already recorded here. Okay, so I'd like to show that so that tells us this, and so we know from above we know well. Okay, so we know that the contribution from near the center of vorticity consumes almost all of the available integral of omega and r squared omega, and so this tells us that the other part, the complementary part, has got to be small. We know that the integral of the part out from away from the center of vorticity, the outer part, is less than this, and similarly this is true. Okay, and so I claim that this is enough to give us to show us that the L2 norm cannot diverge logarithmically. And so claim these imply that these imply. Okay, and so in fact we've basically, so here's the argument. So here are the notes which are not quite finished, but almost finished. And so we basically proved this already. So when but I didn't really highlight it. And so I've reorganized this stuff to highlight the fact. And so when we prove this, oops, let's see. So when we prove the vorticity concentration theorem, here it is. Right, so this is the vorticity concentration theorem. We assume some things. One of the assumptions is written up above. There is this normalization condition. we assume this and these conditions, and we get these conclusions. And in the course of the proof, we actually showed, so I've rearranged the proof, but in the course of the proof, we showed a kind of a upper bound. So we showed that under the above assumptions, first of all, the energy is bounded above by some simpler energy. And then we proved that an upper bound for the simpler energy. The simpler energy is bounded by 1/2 log epsilon plus this stuff. Okay, so in these conditions, so we gave all these arguments. They're all elementary arguments. So here I assumed that the integral of omega and the integral of r squared omega are both equal to 1. And so what these arguments show is that, in fact, if I know these conditions, and I have this upper bound on the strength vorticity, then this implies an energy upper bound. It implies the upper bound on the L normal velocity. And so what I claim is that if we change this constant 1 here and here to different constants, then well, okay, let's do it. Rather, let's look at it. So, okay, so the point is, so I put some exercises here if you're interested. And so, so here's, and so the point is that I want we can check that knowing how conditions like this with gamma, if gamma is 1 and gamma r squared is 1, if I have a general gamma at r that's consistent with the vorticity of string gamma at a distance r from the origin here. And so we've proved things on the assumption that gamma is 1 and r is 1. And the point is, well, you can just change variables. And then, so change variables like this will transform assumption 184 to assumption 1 to our earlier assumption. Then we can see how the energy transforms. We can see if the upper bounds transform, and we can get things like this just by changing variables from earlier arguments. Okay, and so the claim is that, in fact, by just these easy change variables and by things we've already done, we have proved what I asserted we need, what I asserted here, that if we have upper bounds on the integral on the total of vorticity omega and the integral of r squared omega, the impulse I believe it's called, if these are small, then the L2 norm is small. And so that's, and anyway, this is believable. So we saw before, if these are both of order 1, then the energy can be of order log epsilon. And so here I'm saying if these are both a little O of 1, then the L2 norm should be a little O of log epsilon. Okay, that's a totally reasonable assertion. Okay, and so then, so what that says is that when we're looking at this thing, this U epsilon, then we can ignore this for purposes of studying this quantity. I can replace U epsilon by U epsilon I. I can look at in other words, the velocity generated only by the part of the vorticity within a distance epsilon log epsilon of the center of vorticity, which I know is all but a vanishing small part. Okay, that's the first step. Now, I want to simplify things still further. Let's see if I can, here's what I had intended to do. Let's see if it works. Well, I'm gonna have trouble, but I forget that. Okay, so so next, so now we're looking at this expression in terms of the derivatives are grad of And what I've said so far is we can concentrate on the part of the velocity who's generated by this the vortex in this nice small ball. Okay, and so now let's write. And so I'm just slicing off pieces. I sliced off one piece. I'm going to slice off the next piece. Now we'll write, say, U epsilon I is capital U plus, well, okay, U epsilon I tilde. Where, and so the capital U epsilon I is going to be the main piece, and the other piece I'm slicing it off. So okay. Well, so in this is the piece where I'm just going to pretend I have the BS of our kernel as it would be on the plane. So that would be x minus x prime. This is at a point x. Okay, so I'm entering only over the small ball. Yeah. And then U epsilon I, the O is, well, it's the difference. So we have this, I think we wrote it before as maybe R prime, I think, K axisymmetric, which is a function of X and X prime. So X is RZ, X prime is R perp Z perp. X prime is R prime Z prime. Okay, so I think that's the right formula. There was some convention about where we put these R's or R primes. Okay, and so earlier I stated a lemma. I discussed this on last week when I was talking about these things, which said, right there it is. So this axisymmetric BS of R kernel is multiplied by this R prime factor. And so this is really the integrand that appears. It's the planar BSR kernel plus error terms. And okay, and I told you the idea of this, which is, we just rewrite this expression by adding, subtracting. And so we get a piece that looks like x perp, or x minus x prime perp, with some integral. And then you have to evaluate the integral to the best, as best as possible. And then you get another piece. Okay, and so again, as I said, I copied the statement of the lemma from paper from Markov and Buta, or sorry, from Buta and Markov. And they don't really prove it, and the thing they refer to doesn't exactly prove it either. And so, but anyway, I have computations in the notes that show not exactly this, but they show what we need to finish the proof. Okay, and so they show that the main piece is, well, let's say it's so what we really show is something like C times plus well, terms who are bounded by 1 plus log of 1 over x minus x prime. I think we have error terms of that form. Okay, and so then we discussed the idea last time, and it's so again it is sort of a simple rewriting, and then you have to estimate some integrals, and then let's see where I am. Okay, and so the point is we have bounds for this via the stuff I've just discussed. And I don't remember if this is true everywhere, but you see, when we look at this integral, the this term is 0 off a compact set, and so we don't care what asymptotics of capital U, of U for large values of X. We don't need to worry about a compact set. And so on a compact set, this is certainly true on the support of, or say for X in the support of phi and X prime in the support of omega epsilon I. Okay, and so then it's pretty easy to take care of this too. And so then, the integral of U epsilon, and this is a tilde. And all I need is that it contributes, that the contribution from this piece is sort of vanishingly small as epsilon goes to 0. And so again, we can see why that's got to be true, because you see here I have a kernel who's pretty singular. It blows up like 1 over X. And so if that kernel fails to be in L2, for example, on the plane. And here I have a kernel who's almost bounded. Log is almost a bounded function. It's in every LP space for p less than infinity. And so what is this? Well, this is, so for example, I can say, the integral, let's say, is the support of phi, which is all I care about, because I'm eventually going to do a Holder, a Cauchy-Shorten inequality, where I'm multiplying against phi, against rows of phi, and so R is bounded, and then this is just less than the integral of, well, let's call this, I don't know what, F star omega. So it's a convolution. Over log, where f of x, y is a constant, or f of x, sorry. Okay, and so then this will be less than, say, f L2 and times the character function of the support of phi, or of some set. Okay, if I look up here, X is in the set, X is in the support of phi, X prime is in this little ball, and so the distance between them is bounded. And so I only need to consider pairs X and X prime who are bounded with, who are, such that X minus X prime is less than some constant C. And that means I can look at this thing research as some bounded set. And then that has finite L2 norm. 1 squared divided by log epsilon. And this goes to 0, as epsilon goes to 0 because the L1 norm is bounded. And this is a bounded thing divided by log epsilon. Okay, and so I'm really helpless without my glasses. Okay, so U epsilon I tilde goes to 0. And so now we consider in rather so now we consider, well, the same expression, except we can replace the little u epsilon I by capital U epsilon I. And we know exactly what that is. So capital U epsilon I is at a point x is x minus x prime perp over this x minus x prime squared times 2 pi times omega epsilon I, just saying we're a small ball of x prime dx prime. Okay, and our task is to understand this integral. And again, so we've sliced up these pieces. Let's see. Okay, if you remember from like in the first week or two of the class, we looked at this kind of explicit example where the vorticity is concentrated in a small ball, and we said, so we said that outside that ball, what's it look like? And our conclusion was that it looks like the bios of our kernel. So if I have a small ball at the origin, a ball of radius, say little r, and I look outside here, I look at distance 2r from the origin or farther away, the vorticity will look like the bios of our kernel. Say I look at the total amount of vorticities in that ball, let's call that gamma. Outside here, we'll just look gamma times the bios of our kernel, so this rotational flow with angular velocity exactly gamma over distance and purely rotational. It will look like that up to errors of order r, the radius, over distance squared. So we know that we have seen that, and so that tells us that u epsilon I of x is equal to, say, the total vorticity, which is gamma I, the total vorticity in the small ball, I always standing for inner. And then we look at the, so the center is this x epsilon. There's always a factor of 2 pi. And then the errors were plus O of epsilon log epsilon over x minus x epsilon squared. And this is true if x minus x epsilon is bigger than 2 times epsilon times log epsilon. So again, the picture here is that we have this x epsilon, and omega epsilon I is lives in this ball of radius epsilon log epsilon. By construction, we confine it to there. And if we look, say, and so as soon as we're, say, as soon as our distance from the center is twice the radius of the ball, we have a decent approximation by just the bios of our kernel. As soon as we're out here, okay, and so we can then say that let's call this K, or K epsilon I. So one can check that, again, the difference between capital U and this K epsilon I, if I square it and integrate and divide by log epsilon, again, that will be vanishing as epsilon goes to 0. U epsilon I minus K epsilon I squared over log epsilon. Here I have to make sure I stay away from the center of the ball, so I don't know what's going on. So I need x minus x epsilon to be bigger than 2 epsilon log epsilon. This then this the integral of the numerator is what is it? So I'm integrating from some, so they say r epsilon is epsilon log epsilon. So this quantity, I'm integrating something that's like a r epsilon over x squared. I square that, so I'll get r epsilon squared over x to the 4th. I integrate from 2r epsilon out to distance of order 1, say. And what do I get? So I have x to the minus 4, or say r to the minus 4 times r dr. That'll give me r to the minus 2. R to the minus 4 times r dr. I integrate, I get r to the minus 2. And then I multiply by, and then I evaluate that at 1 and at r epsilon to the difference. So the leading contradiction will be r epsilon to the minus 2. But that's what I have in the numerator. And so when I do this integral, I get 1. I guess in the order 1. I divide by log epsilon. This goes to 0. Okay, and so now I have this K, what was that? K epsilon I tensor, K epsilon I, and then d r d z. And so here this is if x minus x epsilon is bigger than 2 epsilon log epsilon, plus some stuff from here. And here I can't replace the capital U by the capital U by the K. Okay, and so this we can do this explicitly. This is a totally explicit, or rather, let's see. So here's where we have this. We go back and remember there's this. We divide the domain into a region. So this is the supportive phi has a region where this grad perp phi over r, where phi is linear. So the point is when I carry out these differentiations, I can differentiate. So the outer gradient can either hit phi and then have just a second orders of phi, or else I can hit the 1 over r. And so the terms involving second orders of phi are supported out here in the region we call B, I believe, before. And the terms where I hit r, that's going to involve only first orders of phi. But then everything is totally explicit. I know the gradient of phi is just 0, 1. The r derivative is 0, the z derivative is 1. and I know what the gradient of R is. It's just the gradient of R to the minus 1 is minus R to the minus 2, comma 0. And so this is totally explicit. And so this ends up being just the L2 norm of a component of this K, and K is totally explicit. We can do that. We can do that in the center region, and then away from the center region, we can see easily from this asymptotics that the contribution again is lower order. And so then we only have to worry about the last term here. And so this is equals the integral over A plus an integral over B. And this is totally explicit. Or rather, do it over a ball, an angular region in A. So I can use polar coordinates, and then that will already consume, that will already give me most of the energy. And then and this is small. And so this ends up being, again, a little over 1 term. And this will give me 1 over 4 pi plus little over 1. So so a way to do this here is to integrate over annulus from, okay, we have to start at a radius 2 epsilon log epsilon. And then let's see, I have to make sure I don't go all the way out to, I have to stay inside of this region A. And so if I go to like 1 over log epsilon, not too far, then what I need is, I need to integrate over annulus where the integral from the inner radius of the annulus to the outer radius, when I integrate 1 over r dr, so I get log of outer radius over inner radius, I want that to be log of 1 over epsilon. And so I need the inner radius to be smaller than any power of epsilon, and I need the outer radius to be bigger than any power of epsilon. Right, so epsilon log epsilon is smaller than epsilon to the alpha for every positive alpha. And if I look at out here, the outer radius is 1 over, like 1 over log epsilon, for example. That's bigger than epsilon to the alpha for every alpha. Okay, so anyway, you mess around a bit, but it's just an explicit computation. And then we have to worry about this last piece. What about that? Could there be extra energy there that's going to throw me off? And the answer is no, because the last piece is negligible because we already know what the total energy is. That was in our assumptions. The integral of right. So the total energy as it appeared in our assumptions was the integral of pi times r times u squared dr dz over the half plane, and that was assumed to be of order. That was 1/2 times log epsilon plus bounded terms. And so the total, and so once you account for factors of pi appearing in different places, our assumptions apply. That the integral, let me see this. Is over log epsilon, I think was 1 over 2 pi plus a little over 1. Okay, so our assumptions implied that, and so and up here we've already and so we've shown that little u and this capital U and this capital K are basically up to lower order error terms. They're sort of indistinguishable when I look at L2 norms. And so when we look at capital K, we found that okay, I wrote this for the this ends up being the L2 norm of the R component of capital K. And but you can do the same computation with the L2 norm of the Z component. And so when we do these computations, we already account for 2 pi energy when energy is in this sense 2 pi when I integrate the L2 norm over, sorry, 1 over 2 pi. We've already accounted for all this stuff up to error terms that are this big. And so the piece we didn't take, the piece we didn't estimate so far, well, there's nothing left. It's got to be little of 1. And so that's how the argument goes. And so I'll post notes shortly. They'll probably be full of typos and stuff like that. And hopefully no terrible mistakes. But again, it's a bit messy, but the idea is pretty straightforward. We want to just we want to take advantage of the fact that we know that this vorticity is concentrated. And so we first replace this vorticity, which has a concentrated part and instant spread out part. We just say we can throw away the spread out part, and we're still okay. And then we want to reconstruct the velocity from the vorticity. We say, well, we can pretend it's like the BSR kernel on R2, and the errors we make will again be lower order. And anytime we do this, you can sort of see before doing any computations why indeed the errors will be lower order, because, well, almost all the vortices living in this ball, the contribution to the energy from the other stuff has got to be small. Or the BSR kernel really is the one on the plane plus lower order terms. And so the contribution from the lower order terms is going to be small. And so we're just arguing this way, and it gets a bit messy, but nothing is super hard conceptually. It's just some details to take care of. Okay, and so I'll get that posted online within, hopefully later today and within a day or two for sure. And then we resume with the normal schedule next week. And so I think yesterday was the only class in this term that will be fully canceled. Next week is a holiday for undergraduates at the University of Toronto, but not for grad students. And so we'll have lectures next week as usual. Okay, any questions about anything? I'll wait for a few minutes to see if anyone has anything to say. And hopefully I'll have new glasses by, they said, tomorrow or Monday. So I'll be able to function better when I have them. And let me say, I sort of, my original plan was to, so the next theorem in my original plan was, so all these things I've been discussing recently are theorems of Markov and collaborators. And so this theorem we've just finished says, solve the axisymmetrical equation of vorticity concentrated around a ring. It stays concentrated and it tells you the velocity. And okay, I didn't do this, but by rescaling, you can see that if the velocity, that if the ring is, you mean that the, for a general circulation gamma and radius r, the velocity is gamma times 1 over r. So smaller rings move faster. The next Markov theorem is one that says, now consider several rings of different radii. Say R1, let me just think of 2, because I have 2 hands. Radii R1 and R2, who are disintegrated. And so the theorem just says, well, the same thing's true, that the 2 rings move with the same intrinsic velocity, 1 over radius times the vorticity strength, and to leading order, they don't interact. So we have, so a small one will move faster than the big one, and and they just, to leading order, they don't interact. There's this leapfrogging phenomenon that I keep on talking about, which involves rings who are quite close to each other. So to see interaction between them, which gives rise to this leapfrogging, they have to be quite close to each other. That's a theorem that has not been proved via the Markov arguments. And so I was going to do that. It's kind of interesting. It's sort of technical, and we're running out of time in the term, so I'm going to probably move on to other stuff instead. I think I'll say a few more words about this result on Monday. Like a thought just crossed my mind. What was it? well, maybe it'll return to me. Okay, so that's the plan. And okay, so if there, well, again, I'm happy to wait for questions. In the meantime, I'm going to check and see if there's a president in the United States yet. Or Lars, do you have a question?
I enabled my microphone by mistake, but
okay,
as I did, let me ask you. So essentially, that's really a 2D argument. So what you do is really comparing this solution, say U epsilon to the 2D. What would be the 2D solution to the coming from the 2D Biot-Savart kernel, and then step by step you kind of get rid of the error terms. Say first by this expansion you were talking about, inspired by the one by Markov and collaborators, and then say we had these other error terms you were denoting with capital letters.
Yeah. So here's what's 3D about it. And so okay, so the basic identity we use is, so if I had the real Euler equations, I would have the same identity, but without all these factors of R. So I would have the grad perp phi, and then U tensor U. And here I'm really writing T. And for axisymmetric, it's this thing I wrote a bunch of times, R grad. And here I have to use the tau variable. Right, and so what's true in both cases is that, and so this U tensor U over log epsilon, well, U tensor U is UI. So this is the, well, it's U1 squared, U1, U2, U1, U2, U2 squared. Okay, it's this matrix. And so what happens here is, in both cases, one can phrase the proof. We didn't do it this way, but this is how you do gross potatoes. You can phrase the proof by saying, well, we know something with the vorticity, and we want to use that to understand what this looks like, and then use that to understand what the right-hand side identity is, and that'll tell us how the vortices are moving. So here there are two terms. Here there's a term as above. And so when I expand this, I get two terms, and one is exactly above, but that turns out to be the lower order term. We ignored that, we threw that away. And so, and that's somewhat responsible. Here I had to rescale in time. I had to have this tau variable. Here I didn't. Here this original T, because somehow the new, you see, if I only had this term, I could take the kind of test function I described, and it would totally vanish at the vortex core. If the second orders or if I have something who's linear near the vortices, then these intervals are really supported away from the vortices, and things are so much smaller. And so, right. So in the end, so the reconstruction of U from the vorticity, yeah. So the argument there as well, that's close enough to 2D. We can pretend it's 2D. But and so the place where the differences appear are in these earlier identities that we're relying on. Right. Yeah.
So the key is that you don't have you don't have really the argument that the second derivatives kill the affine test function. So this is where this error
right.
term comes from,
Yeah,
say,
that's right.
heuristically.
So, yeah, that's
so we run into this trouble, even though, say, R is always of order 1. So this term is not, say, doesn't say the fact that it's 1 over R doesn't create problems. Say R is never close to 0, but still this
yes,
term turns out to be
exactly that there's no reasonable test function for which this is supported away from the vortex core.
Yeah.
I mean, or I mean, if you had a function like that, it would be constant near the vortex core, and then if I have a function phi who's constant in the vortex core, when I multiply by phi and integrate against omega, that's like evaluating phi at the place where the vortex is, and so such a function will not tell me where the vortex is. It'll move around and I'll get the same value. And so, right, and so yeah, that's the key difference.
Thank you.
Well, yeah, thank you for the question. Yeah, the point I was going to say earlier is that, well, I mean, we should have finished a while ago, but since people are still here, I'll say this. So remember, in this 2D theorem, actually, one thing is we never mentioned the energy. We never really mentioned the L to norm of U. And our assumptions allow the L to norm of U to diverge at a crazy, crazy rate. So we assume that for some p bigger than 2, that the LP norm of U was like epsilon minus gamma, for some gamma. And so here in the 2D theorem, it could be the case that the energy is way, way, way bigger than log epsilon. And still the proof is valid here because it's the velocity, and the point is there, no matter how big it is, the leading order dynamics from the vortex core are purely rotational, and so you got to be able to ignore that, even if there's a ton of energy there, if it's extremely divergent. In this ring theorem, the velocity is really the energy. The velocity is the L to norm of U. That's how fast it's moving. So that's where log epsilon. That's why it's moving with speeds log epsilon, and that's exactly because when I do this computation, I have this non-vanishing stuff multiplying the quadratic terms in U, and so and that's what's telling me how the vortex is moving. And so that's another difference between the 2D and the axisymmetric case.
Okay, thank you. I see it. That's this makes quite a huge difference.
Yeah, it does.
Yeah. So it was really reductive to say that's kind of 2D similar this.
Well, there's certainly similar ingredients, and yeah, some of the point is, in the end, this right, the divergent part of the energy is concentrating in a small neighborhood, a little over one neighborhood of this vortex core. And so on small scales, you can sort of forget the spatial inhomogeneity represented by this function R, the variable R. And that's why you can approximate it well by the 2D BSR kernel. But in many ways, it's different. Okay, anyone else? Okay, so anyway, have a nice weekend, and I'll see you on Monday.